The graph below shows the results of 3 experiments in which dilute hydrochloric acid is reacted with marble chips, which is calcium carbonate. Details of the experiment are given in the table below. So each time they tell us that they use a certain volume of acid, and we know from rates of chemical reaction that when you put a different volume of acid, so they're my marble chips, if I put in 20 moles of acid, this is the reaction sites. If I put in 40 moles of acid, it makes no difference. If I put in 75 moles of acid, it makes no difference to the reaction site. So the volume of the acid shouldn't really make a big difference. The temperature does make a difference to how fast, because remember we're looking at time, the volume of gas released versus time. And we do know that we are putting calcium carbonate and hydrochloric acid together. And we have learned before that an acid and a carbonate gives me a salt plus water plus carbon dioxide. Not that it's essential to know that, but just the fact that you've then got an idea. You're going to be making carbon dioxide, and the faster the reaction's taking place, the quicker this volume of carbon dioxide will go up. Match the graphs to the experiments in the table and give experiment numbers that correlate to each curve. So firstly, we've got whole and powder. Powder is definitely going to go faster than some of the others. And the other thing that you're going to take a look at is the temperature. 3 and 1 have a higher temperature. So the fastest of all of these is going to be number 3. So the fastest reaction is A. So A is number 3. Then the next fastest is the one that's going at a higher temperature. And that is going to be B, which means that we are going to land up with number 1 being B. And finally, when I've got less volume, notice that at the end of the day, these two with the higher volumes of acid landed up, even though it took longer for B, they landed up with the same volume of carbon dioxide. C not only is going to go slower because it's colder and it's whole pieces of calcium carbonate, but it also won't give me as much carbon dioxide at the end of the day either. It's going to terminate sooner. Why? Because there was less hydrochloric acid to react. So this one is going to be C over there. Which factor remains constant in every experiment? Well, if you look at the table, absolutely nothing stays constant in every experiment. What probably does stay constant in every experiment is the mass of calcium carbonate. That hasn't changed at all. They also say it is dilute hydrochloric acid. In other words, it has the same concentration. So you could have either told me the concentration of the hydrochloric acid does not appear to change, or the mass of the calcium carbonate does not change. Which graph represents the fastest reaction rate? Provide an explanation for your answer by referring to information in the table. So the fastest reaction rate is going to be graph A. And the reason it's going to be graph A is because we can see that it is representing the highest temperature and the greatest state of division. You had to refer to the table, so you had to know that graph A was number 3, and I gave some marks for saying something like it had the steepest gradient, or made the most carbon dioxide in the shortest period of time, and then you had to say highest temperature and the greatest state of division. In other words, it's powder, not chips or whole. The reaction between zinc and dilute hydrochloric acid can be represented by the following reaction. 1 gram of zinc granules is placed into a flask with a certain amount of hydrochloric acid. They give you the concentration. The mass of the flask and its contents are measured at regular time intervals. So firstly, this is what you had to start with. That's a solid and an aqueous. As the reaction proceeds, my one product leaves the flask. It's a gas. So the products, more product means that is going to be lighter or less mass versus this one, which is going to be heavier with more mass. So draw a sketch graph of the relationship between mass of the flask and its contents over time. So you have to still label your graph mass, and it's reasonable to decide that you're going to use grams because, well, they've given it to me in that, but that wasn't a big thing. Time, any unit of time, and the mass decreases as that reaction proceeds. Any evidence of decreasing, if you had a bit of a curve, that was also fine. In this reaction, is this reaction endothermic or exothermic, and how did you know that? Delta H over here is negative. That is a exothermic graph. Draw a sketch energy profile to represent this reaction. Label the energy of the reactants, the energy of the products, the activation energy, and the heat of the reaction. Ensure that your axes are correctly labeled. So, the first thing is you need to draw an exothermic graph. Energy of the products is less than the energy of the reactant. So the shape counts. This is your potential energy. This is not time. I didn't mark you down, but it's actually reaction coordinate. Or you can sometimes say course of the reaction. This is the energy. It says label energy of products. Some of you just wrote products. I accepted that energy was on the axis, but this is energy of reactants, not products anyway, but anyway. But you were asked to label energy of reactants and energy of products. It then asked you to give me the activation energy. That is the energy from the energy of the reactants to the top of the activation curve. And finally, it wanted you to give the heat of the reaction, that's your delta H, which is the difference between the energy of the reactants and the energy of the products. That should be guaranteed 6 marks. The following results were obtained when the rate of the decomposition of this substance into those two was investigated. The reaction took place in a flask of fixed volume. That's going to become interesting later. Time goes on in seconds. The concentration, you will notice, is decreasing of the reactants as it turns into product. Write down a suitable investigative question for this investigation. I wasn't overly strict. I was kind of just looking for a question that said something about that and those. But you should ideally say, how does the concentration of SO2Cl2 change over a period of time? I should have the words of concentration and time, independent and dependent variable, in my question. So we would like ideally to have, how does the concentration of SO2Cl2 change over time? Identify my dependent variable. In other words, what am I measuring? I'm measuring the concentration of the SO2Cl2. That is my dependent variable, and I would have liked to have seen the word concentration, not just the square brackets. Identify a variable that must be controlled. They've told me that they've kept it a fixed volume. Control the fixed volume. That's what they've told you. It is not going to be a constant temperature because this is an exothermic reaction. It's going to be hot, get hotter all the time. So you can't control the temperature. On the axes provided on the answer sheet, draw a graph of that. So you need to give me a heading graph of whatever's on the y-axis versus whatever's on the x-axis. Label both your axes with a unit. Give a constant, what's the right word? Scale. Constant scale over here. Put your 0 onto the point of 0, and then put your points in and join it with a smooth line. Describe how the graph may be used to calculate the instantaneous rate of the chemical reaction at 2500. You were able to, and most of you did this really nicely, by the way, you were able to draw a tangent. It was a description. You didn't have to actually do it. Draw a tangent at 2500 seconds and then determine the gradient of that tangent. using collision theory, explain the change of reaction rate during the course of the reaction. As the concentration of SO2Cl2 decreases, there are less particles available to collide. Therefore, rate decreases. Use the graph to predict the time taken for only 0,3 moles per cubic decimeter to be left in the container. You go onto the graph at 0,3, you come down, and it's approximately 1,500 seconds. If you gave me 1,600, that's okay. Well, it's a ballpark, but you had to show what you were doing there. And the curve would be, describe how the graph would change if a higher temperature were used. You would land up with the whole reaction going faster, and therefore what would you say? The curve would be steeper and reach completion earlier or at a shorter time.